This is lesson 11.3b, continuing a discussion of how to get something into its simplest radical form. So the next thing we need to talk about when we're talking about simplifying radicals is that the root of the sum and the root of the product are different things. Okay? In fact, let's just go ahead and write that down. The root of a sum and the root of a product are not the same. Okay. Once again, addition and subtraction and multiplication and division must be treated very differently. They are different. So this is example number 5. It is not tied to a rule number 5, but here it is. The root of a sum and the root of a product are not the same, unless you want to call that statement rule number 5. Okay, the cubed root of 8 plus 125. Let's look at that, and let's look at the cubed root of 8 plus the cubed root of 125. Okay, on the left-hand side here, we have the cubed root of, if we add 8 there, we get 13, 3, and 1, 133. Okay, which you can't get an exact answer for. If you get an approximate answer, and if you round it to the 100ths, I believe it comes out to 5.10. However, on the other side, if you try to break this up like this, you're going to get the cubed root of 8, which is 2, plus the cubed root of 125, which is 5, and that's equal to 7, and those are not equal. Okay? And the reason for that is there is an addition there. If it were a subtraction, the same thing would be true. You have two terms under the radical. Okay, however, let's call that bad example A. Okay, here's the good example. Okay, if you have the cubed root of 8 times 125, then you can break them apart. The cubed root of 8 times the cubed root of 125. Okay? Actually, let's go ahead and I'm not going to use red for this. I'm going to use green. Okay? So if we take the cubed root of 8, which is 2, and the cubed root of 125, which is 5, and this is an understood multiplication between them, then we get 10. Okay? On the other side, if we do the cubed root of 8 times 125, will give us 1,000. Okay? And 1,000 is actually, you remember this, there are 3 zeros here. That means 1,000 is equal to 10 cubed. And the cubed root of 10 cubed is 10. So yes, these are equal. That does work. Yay. Okay. If there's a multiplication, you can use it that way. All right, let's move on to an example 6. Okay. What if we look at the cubed root of 48? We've looked at that before, right? And we have broken it apart to analyze it. So 48 is 16 times 3. So we can break that into the square root of 16 times the square root of 3. to get for square root of 3, since 4 is the square root of 16. Okay. 7, example 7. The square root of 36x cubed y to the 5th z to the negative 2. Okay, so let's get rid of that negative first. I'm going to rewrite this as the square root of 36x cubed y to the 5th over z to the positive 2. That negative exponent has driven the base of z to the denominator, and the exponent has become positive. So now let's take a look at what we have here. We have 36 is equal to 6 squared. X cubed is equal to x squared times x. And, okay, think about this one for a minute. Y squared is y to the 4th. Okay, because 2 times 2 is 4. And y to the 4th times y will give us this y to the 5th. Okay. All right, and then in the denominator we have our z squared. So taking the square root of those that we can and bringing them outside, we're going to have 6 squared, we can bring out a 6. Taking the square root of 6 squared. Taking the square root of x squared, we get x. Taking the square root of, well, okay, the next x we cannot take a square root of. So we'll move on to this y squared squared. So since the y squared is itself squared, we bring out a y squared. That leaves underneath the radical xy. And we divide by, look at this. We're taking, now, it's as if we're taking the square root of that z squared in the denominator to give us c. And that's as far as we can go. It probably would have been more helpful had I written this very specifically. Erase a little bit of that. Like this, with 2 radicals, one over the other. But I hope you can see that it doesn't matter which way I wrote it, it still works for us. Okay, let's minimize this and move it a little bit out of the way. And I'd like to write a couple more examples up here, and then we'll talk through them. Okay, to shorten the video a little bit, I've gone ahead and written out my next examples. We will start with number 8. Okay, we're looking at the square root of m cubed. So if you remember, that's equal to the square root of m squared times the square root of m. Therefore, the square root of m squared is m, and we can't do anything with this square root of m that remains. So that would be our final answer for that one. If you look at number 9, we're going to be doing the same thing. The square root of m squared times the square root of m is what you get from, let me change color there, m cubed. Okay? But you still have this square root of m remaining. Nope, not that color. Okay? So we have this equal to the square root of m squared is m, and then square root of m times square root of m, well, that equals m as well. So our final answer is m squared. Could we have gotten that a different way? Yep. Okay, m cubed square root of m is the same thing as the square root of m cubed times m, or the square root of m to the 4th, which is equal to m squared. Okay, either method will get you there. You're just applying the rules that we've been learning in slightly different ways. Okay, let's take a look at the cubed root of 16. Cubed root of 16. Well, do we have any perfect cubes that are factors of 16? Yep, the one we've been using again and again today. The cubed root of 8. And you multiply that by 2 and you get the 16 that is the radicand. So we can break that up as the cubed root of 8 times the cubed root of 2, or 2 cubed root of 2. Okay? If we started at a different place, if we started with the cubed root of 16 multiplied by the cubed root of 4, if that was our original problem, we could look at it like this: the cubed root of 16 times 4, okay, which gives us the cubed root of 64. And the cubed root of 64 is 4. 4 times 4 is 16, times 4 is 64. Please take a good look at these last 4 examples, because in the next video we're going to be moving on to rationalizing the denominator and then to reducing the order of a radical, and we will be using the techniques we used here to do those things. See you in video C.